Welcome to the Ninja Academy, where we learn about the most vital part of being a ninja, our life force, chakra. So in the world of Naruto, chakra combines physical and spiritual energy and is a vital element for survival that flows through meridians or pathways, right? That's going to enable ninjas to execute powerful jutsu or techniques. Similarly, in electrochemistry, our life force is redox chakra, entailing the dynamic technique of oxidation and reduction, or redox reactions. Without chakra, there is no ninjas, and without redox reactions, there is no electrochemistry. So understanding redox reactions is pivotal, and the electrochemical cells we delve into operate on the principles of these reactions. As we venture into our hidden chemistry village and the Ninja Academy, we not only master the art of balancing redox chakra, but also learn to use our knowledge to navigate through different ninja lands. Luckily, you may remember redox reactions from ancient scrolls in Chem 101. So this is pretty much review, but we will be adding a new jutsu/technique to balance next. So that may be new for some of them. Let's go ahead and review what we know. From Chem 101, we know that oxidation is going to be the loss of electrons and reduction is going to be the gain of electrons. And these processes are going to occur simultaneously. And to map oxidation states of elements and compounds, we assign oxidation numbers to a chemical reaction, for example. So we have to use the oxidation number rules or rules for assigning oxidation numbers that you might have had to remember when you were in Chem 101. Yes, they are coming back, so you will have to make sure that you are reviewing this particular concept and go ahead and do some practice problems from previous chapters. This is going to run you around chapter 4 for our book, okay? Now, of course, we're going to be assigning these oxidation numbers within a chemical reaction. So here's an example chemical reaction. We have zinc solid that's going to be mixed with a strong acid that's going to provide 2 protons here. Okay, that's going to form zinc aqueous and H2 gas. And we can visualize that in this test tube here. We're going to have zinc solid here. It's in an acidic solution, which is going to provide our 2 H pluses. And as this overall zinc continues to break down when it mixes with this acid, it's going to form these bubbles, which is going to be H2 gas. And of course, a zinc 2 plus is going to be aqueous, which we cannot visualize in this clear solution. Okay, folks? Once we use the rules for assigning an oxidation number, then we're going to apply them to each of the species that we see in the chemical reaction. We make sure everything is balanced. And then what we usually do is we draw lines to show oxidation and reduction. So here we go on from 0 oxidation number to +2, which means that we have lost 2 electrons here. And so we can draw a little line to go from 0 to +2, which means lost. You can even go and say, okay, we lost 2 electrons here. Next, we can look at reduction, which is going to be +1, meaning a loss of electrons, down to 0, which means you had to gain 1. Since there's a 2 in front of it, that means we had to gain 2 electrons. And so, of course, we can say we have gained 2 electrons here. As you can see, the number of electrons lost and the number of electrons gained are going to be equal. And so the total number of electrons lost or gained must equal no matter what when we're dealing with redox reactions or in redox chemistry. What else you notice is that oxidation is going to result in an increase in the oxidation number. So as you can see, we have a loss of electrons here, which is oxidation. We're going from 0 to +2. We've increased the actual integer here. And so when you increase the oxidation number, that usually results in oxidation, right? This is, again, review. The opposite is for reduction. When you decrease the overall oxidation number, that's usually going to result in reduction. So here we're going from a 1 down to a 0. That, again, is reduction. We can even go further and add more terminology like oxidizing agent and reducing agent. So what is the oxidizing agent? The oxidizing agent is going to take electrons from the substance being oxidized. So whatever is going to lose electrons has electrons to give, right? And so the oxidizing agent is going to take those electrons. And so the oxidizing agent is therefore reduced. All right, folks? And then, of course, vice versa. The reducing agent is going to give electrons to the substance being reduced. And so the reducing agent is therefore oxidized, folks. And here's just a cool graphic that kind of summarizes all of this. Of course, you can go back and do review, which is what I recommend. And of course, do a practice problem related to that reviewed concept. Okay, you also want to make sure you know how to assign oxidation numbers and use the rules, because it's considered review and it's something that you definitely will want to know and can be very helpful. So when we look at this overall chemical reaction here, we see that for an atom in its elemental form, it's always going to have an oxidation state of 0. So we have the zinc solid here is 0, the H2 gas here is 0. They're both in their elemental form. This H plus has a charge already attached to it, so that's automatically going to be the charge or oxidation number here. Same thing with the zinc 2 plus, it already has a charge attached to it, so it automatically is going to have a charge of +2 here. It's just making sure you go back and review that portion. Now that we've reviewed redox reactions or redox chakra, let's unlock a new scroll to balance our redox chakra. So in Naruto, scrolls hold hidden knowledge. Some are going to reveal jutsu that ninjas can use with their chakra. We've already decoded the ancient Chem 101 scrolls to review redox chemistry. Now we're going to break the seal of a revered scroll to explore the profound jutsu called the half reaction method. Similar to intricate hand seals in ninja arts, this technique is going to empower us to balance redox reactions in both acidic and basic solutions, demanding precision and strict adherence to these prescribed steps. So the half reaction method literally divides a redox reaction into its oxidation and reduction half reaction. Why? Well, because it reflects their physical separation in electrochemical cells. And we're going to learn the details of that as we go along, but we know that electrochemical cells have to have redox chakra or redox chemistry, meaning there has to be an oxidation portion and a reduction portion, and the exchange or gain and loss of electrons must be equal, right? We learned that and did review of that previously. The cool thing about utilizing this half reaction method is that it typically doesn't involve assigning oxidation numbers. If you follow the steps, then the half reaction method is actually easier to apply in acidic or basic solutions. Now, of course, this is going to be in cases where the half reactions are easy to understand and separate. If you have situations where they're unclear to you, you can always use the assigning oxidation numbers portion, but we're going to be focusing on the half reaction method here. Let's get into our steps. Okay, so step 1, we're going to divide the skeleton reaction into 2 half reactions. That means whatever reaction you're given, you're going to look at the initial species and then basically divide them into similar species reactions. So for example, if I'm giving like a bromine on the reactant side and another species that have bromine on the product side, then I would probably group those into one. And then of course, whatever's left over will be grouped into the other species. Now, you're not going to know up front if something is oxidized or reduced. So again, when we get into an overall example, you'll see what I mean by just grouping them into 2 half reactions up front. After that, we get into step 2, which parts are letters A through C we've seen before with our overall understanding of balancing redox reaction. So of course, you're going to balance all atoms that are other than oxygen and hydrogen, balance oxygen by adding water, balance hydrogen by adding H+, okay? And then you're going to balance the charge by adding electrons. This is going to be the step or the reason why we do not have to assign oxidation numbers. Now let's get into this portion. So in reduction, we know we are gaining electrons. So how do we verify which one of our half reactions in step 1, whether or not it's oxidized or reduced? It's going to be based on this letter D portion. So in this portion, you have to make sure that the charges are equal to 0 on both sides. So in reduction, your product side is usually going to have a charge of 0, and your overall reactant side is usually going to come with some excess charge. So if you have 2 H+ or 2 positive charges on this side, that means you're going to need 2 negative charges to balance it out to be 0. So you need to make sure there's 2 electrons on the product side. If there's 2 electrons on this portion side, then you're going to have 0, which is going to equal to 0, again, balancing out everything for this overall half reaction. And if that's the case, and you are putting electrons on the reactant side, then you are looking at an overall half reaction that is being reduced or a gain of electrons. Vice versa with oxidation, we know it's all about losing electrons, but we have to verify which one of our half reactions are again doing that. So if you have a neutral charge on your reactant side and you have charge left on your product side, then you have to look at the amount of charge you have and balance it with a certain amount of electrons. So I have 4 positive charges here. I need 4 negative charges to balance it out. So I'll put 4 electrons on this side. Because I'm putting electrons on the product side, that is how I'm verifying that this half reaction is oxidized. Okay, folks? And so as you can see, I have 0 charge on this side and 0 charge on this side. And so everything is going to be balanced. Once everything's balanced, you go to step 3. And if necessary, you multiply one or both half reactions by an integer so that the number of electrons gained or lost are going to be equal. So if I have a loss of electrons 4 here and a gain of 2 electrons here, I must multiply this half reaction by 2 in order to get an equal number of electrons. And then what you do finally is going to be adding up both of these half reactions. Canceling species that appear on both sides, and include the state of matter like gas, aqueous, liquid, solid, etc. That's going to be step 4. Next, you're going to check that the atoms and charges are balanced, and that includes our 5 steps. Now, you might be saying, hey, what about 4 basic? What is this blue step right here that's boxed off? Well, we're going to hold up on that first. Everything I've told you here, steps 1 through 4, and then step 5, represent how to balance redox reactions in acidic solutions. Okay? Every way, anytime that you're trying to balance, no matter if it's acidic or basic, you're always going to do these steps. So the way my brain works is I always remember all the acidic steps, and then if it's basic, I just add a step at the end. Okay? So acidic, you're going to do all the steps 1 through 4, and then jump to step 5 here. If it's basic, you're going to do all these steps 1 through 5, and then at the end, you're going to add this step here, which means that when you have a final reaction that you've already balanced and canceled off the species, you're now going to balance out or neutralize any kind of H plus that's present by adding OH minus to both sides. Now, when you add H plus and OH minus, you have the ability to form water, okay? And so you have to then go ahead and make sure that you're canceling out water on both sides of the reaction as well. So that's if you're balancing in basic. Again, you're going to do all the same steps. You're just adding this last step at the very end. Now, of course, we're going to get into getting into more practice with this overall half reaction method in acidic solutions first, and then go to the training grounds for a full example in the basic solution so we can really get into this jitsu. Let's go ahead and start with acidic solutions first, folks. Okay, let's use our new technique by balancing this reaction in acidic solution. Let's focus on steps 1 and 2, which are all about making sure we separate the half reactions and making sure that the half reaction atoms and electrons are balanced. So remember when I told you in step 1, it's always going to be harder up front for some folks to automatically recognize if something is oxidized or reduced. I always wait into step 2D before I verify what's oxidized or reduced based on electron charge, right? So the way I get around that is I just make sure that I'm at least breaking everything up into half reactions properly. I look at all my species. I have bromine, O3 minus here. I have N2H4 here for my reactants. And then I have Br2 liquid and N2 gas for my product. Again, we are in acidic solution. How am I going to break these up into half reactions? Well, I'm going to make sure I put species together. So for example, I have Br03 minus as a reactant. I'm going to make sure it's going to be next to the Br2, which is also a liquid here. And I'm keeping the states of matter just in case. And then I'll do the same thing on this side. I have my N2H4, which is aqueous. And then I'm going to keep it with the actual nitrogen as well, which is going to be N2 gas. That's what I mean by breaking it up. Do I know the details about redox yet? No. But again, in half reactions, the first step is just getting half reaction. And that's how I go ahead and do it. Next, we are now in step 2, right, which is part A is going to be balancing atoms other than oxygen and hydrogen. So we're looking at Br03 minus here to Br2. Of course, if you're balancing anything outside of oxygen and hydrogen, that's going to be the bromine here. I'm going to put 2 in front of here. That means our bromines are now balanced. Over here, we have our nitrogens. They're already balanced, so there's nothing to do there. Next, it tells us to balance oxygen atoms by adding water molecules. So over here, we have 6 oxygen atoms, because 2 times 3 is going to be 6. So we have to make sure that we're going to add 6 water molecules on our product side. Over here, we don't have any oxygen atoms, so we don't have to worry about anything. Next, it says we have to balance hydrogen atoms by adding H plus ions. So for us, we have 6 times 2, which is going to be 12 hydrogen atoms on the product side. So we need to make sure that we're adding 12 H plus ions on the reactant side. Okay, and of course, that's going to be aqueous here. And we need to do the same here. We have 4 hydrogen atoms on the reactant side. And we need to make sure that we add 4 H plus ions to the product side. Now we've gone to the step that's going to tell us which one is going to be reduced and which one is going to be oxidized as far as these half reactions. And that is balancing charge. So we have to figure out what is the charge on the reactant side and what is the charge on the product side for both of our half reactions. All right, so how do we do that? We look at the actual charged ion portions that are in the reactants and products. So in the reactants portion here, we have 12 H pluses. That means we have 12 positive charges here. And then we have 2 Br03 minuses. This entire thing is going to be seen as polyatomic. So that means we have 2 negative charges here. 12 charges plus 2 negative charges is going to give us 10 positive charges on this side. And of course, for the products, they both have 0 charges. So we want to make sure that these are equal. This side is 0 and this side is 0. So what do we have to do? We have to add 10 electrons to balance out the 10 positive charges on the reactant side. So if we're adding 10 electrons to this half reaction, that means this half reaction is going to be representing reduction, okay? And so automatically this half reaction is going to be representing oxidation, but let's verify that as well. And just let me just go back really quick and say, if I'm adding 10 electrons here, that's going to cancel out the 10 positive charges and give a 0 on this side as well. 0 and 0 is how it's all balanced out. Okay, folks? Now over here on this side, we have a 0 charge on the reactant portion, and then we have a 0 charge for the N2, but we do have 4 plus charges here because of the 4H plus ion. Because we have 4 plus charges here, we want to make sure that we add in 4 negative charges to cancel it out. That means we have to add 4 electrons to the product side. If we're adding electrons to the product side, that represents oxidation. And so now we have 0 charge on this side and 0 charge on that side, and it is going to be balanced, okay? Or at least the charge is going to be balanced. You could have also, for the folks who are still like, I want to use oxidation numbers, you could have definitely gotten the oxidation numbers for bromine here and see that it went from +5 down to 0 to show that it's being reduced. And for nitrogens here, you would have saw that it was going from -2 down to 0 to show that it's being electrons being lost. Okay, folks. But again, I always recommend that you're following the half reaction method just as we see it, because to me it is a little bit easier. All right, now I've basically taken the half reactions that we got from steps 1 and 2. Everything, the charge is already balanced and all that stuff, and I've rewritten it here. I have 10 electrons on my reactant side plus 12H plus 2 BrO3 minus is going to produce Br2 plus 6 waters. Okay, that's for my first half reaction. The other half reaction is going to be oxidation, is going to be N2H4 to break down to N2 plus 4H plus 4 electrons. Now, the next thing we have to do for step 3, because this is where we are, step 3, is to multiply each half reaction by an integer so that the number of electrons lost and gained are the same. That's one of the things that we have to make sure is true. So we have 10 electrons that are going to be gained here and 4 electrons that are going to be gained here. So we must make sure that we have the proper number of electrons. So what we could do is multiply this entire thing by 2 and multiply this entire thing by 5 to get a total of 20 electrons. So let's go ahead and write that out. All right, I then get 20 electrons plus 24H plus 4 BrO3 minus 2 Br2 and then 12 H2O, all because I'm taking 2 and multiplying it by all of the coefficient numbers in front of each species and electrons. Same thing over here, I'm going to multiply everything by 5, so 5 N2H4, I'm going to have 5 N2, 20H plus, and of course 20 electrons. All right, folks? Now, step 4 is to add the half reactions together, canceling substances that appear on both sides, and include the states of matter, and of course, electrons must always cancel as well. So I'm going to basically add this overall reaction, just put it up here so it can look like it's being added together. You can just leave it in a straight line if you like and just go ahead and cancel things out, but I'm just used to the old way, so again, my brain's just doing it this way. All right, and we're looking to cancel things that are the same on both sides. So let's go ahead and look at this. Anything that's not the same, all right, electrons we can get rid of. We know they're the same. It's 20 electrons in reactants and products, so we're good there. As far as H plus, we have 20 H plus here and we have 24 here, so that means we'll have 4 H plus left over on this side. Anything else the same? No. So that means everything else will be brought down. All right, so I'll just bring everything down and that would represent my answer. After I do step 4, all I need to do is complete step 5, which is checking that I have the correct number of atoms in charge and everything is balanced. So when I'm looking at everything on my reactant side, I should have 5 N2H4, 4H plus, and 4 BrO3 minus left over, which is what we have here. I have all my states of matter. Again, I got it straight from my overall reaction. And then for my product, I should have 5 N2, Br2, and H2O left over here, which are 3 products. As we can see, everything is going ahead and verified, and I have all my states of matter. Now, again, we got to check that we have the same number of all the right atoms on each side. So how many hydrogens do I have? I have 20 plus 4, so 24 on this side, 24 on that side. Everything's good. How many nitrogens do I have? I have 10 on this side, 10 on that side, so we're good. How many bromines do I have? I have 4 on this side, 4 on that side, so we're good, right? How many oxygens? I'm going to have 12 on this side, and then I have 12 on this side. We are good. And then as far as charge, we've already gotten rid of the 20 electrons on both sides. So again, the charge should be 0 and everything is balanced out. All right, folks? So as you can see, all we did was use steps 1 through 5. We did not have to add that additional step because we are dealing with an acidic solution. Let's go ahead and see what happened if we did have to add an additional step for this particular reaction right here. All right, so we're going to say that we are starting with the same exact reaction as before, but this time we are going to balance in a basic solution. So that means we can do exactly as we just shown you, and all we would do is be left to this particular balanced reaction, which is going to be the 4H plus, 4BrO3 minus, and the 5N2H4, producing the 2Br2 plus 12H2O and 5N2 gas. Let's see what's the next step would be if we had to balance in a basic solution. All we would need to do is neutralize the H plus, okay? So in order to neutralize H plus, we are going to add OH minus to both sides. How much OH minus depends on how much H plus we have. So here we have 4H plus. That means we're going to add 4 OH minus to the reactant side, and we're going to add 4 OH minus to the product side. Whatever you do to one side, you have to do to the other, right? Now, because we have an OH minus and H plus here, these are going to automatically form, you end up forming 4 water molecules here, okay? Because anytime you have H plus and OH minus in that same vicinity, especially to neutralize, it's going to form water, and that's how the neutralization happens, right? Another idea is if you have an acid and a base, you know it's going to form, of course, water to help you see that there. So the acidic portion is H plus, and the basic part is going to be the OH minus. And so now we form 4 water molecules here, and of course now we have 4 OH minus on the product side. So we can rewrite our overall equation and say 4H2O plus 4BrO3 minus plus 5N2H4 is going to produce 2Br2 plus 12H2O plus 5N2 plus 4 OH minus, okay? Now again, what do we need to do? We need to make sure that we cancel excess water. So as you can see, we have 4 water molecules on this side, and we have 12 on this side. So we basically can cancel out those 4 water molecules, and we'll be left with 8 water molecules on this side. And so our overall answer, if we were to balance in a basic solution, is going to be, finally, 4BrO3 minus plus 5N2H4 is going to produce 2Br2 liquid plus H2O liquid plus 5N2 gas plus 4 OH minus. Again, we definitely want to wrap it up with step 5. Step 5 is always just a wrap up to verify everything is balanced, okay? So we want to make sure we have the correct number of bromines. We have 4 and 4. Correct number of oxygens here. We have 12. And then, of course, we have 8 here and 4 here. So that's going to be 12. And then how many hydrogens do we have? We're going to have 20 here. Then we're going to have 16 plus 4. So that's 20 there. Nitrogens, we have 10. As far as charge, we have 4 negative charges on this side. And we have 4 negative charges on this side as well. So everything is balanced, folks. Again, to me, when you're getting down to the basic solution portion, just adding in the step of course, balancing or neutralizing H plus with OH minus, and then getting rid of water is not too bad. You're still doing the same step 5. Let's go ahead and get a specific example in balancing redox and basic solution at the training ground to, again, make sure we have good enough practice with this jitsu. All right, we're at the training ground, folks, and this is our chance to develop new jitsu and techniques. But first, we want to continue to develop our skill in the half reaction method, this time with an example exclusively in balancing in a basic solution. So this is about balancing a redox reaction in basic solution. Permanganate ion reacts in basic solution with oxalate ion to form carbonate ion and solid manganese dioxide. Balance the skeleton ionic reaction for the reaction between NaMnO4 and Na2C2O4 in basic solution. So how will we approach this? Again, we always want to make sure we break everything up, step 1, into its half reactions. How do we figure out which ones oxidize and reduce? We're not there yet. All we're doing is breaking them up based on species. So I see manganese here, it has to go with manganese oxide here. I see carbon here, it needs to go with carbon here. So that's how I'm going to break it up as far as half reactions. Here are my half reactions based on what is given. Next, we have to go along with step 2, which is going to be balancing the atoms and charges in each of the half reactions. So first, that means any non-oxygen hydrogen. Here, the manganese are already balanced, so nothing there. Here we have carbons. So this is 2, so that means you must have a 2 in front of here, okay? So let me go ahead and make that look better. So that's supposed to be a 2. That's CO3, and then there's going to be a 2 in front of there. Now our carbons are balanced. Next, we're going to balance oxygen by adding waters. There's 4 oxygen on this side, 2 on this side, so we have to add 2 H2O on this side. Over here, we have 4 waters, and then we have 6 here. So we have to add 2 waters on this side to make sure we have 6 in total. Now our oxygens are balanced by adding water. Next step we're going to do is balance hydrogen by adding H+. So over here, we have 4 hydrogens. We need to make sure we're adding 4 H+ onto the reactant side. Here we have 4 hydrogens, so we need to make sure we're adding 4 H+ over on the product side here. Now, as you can see, our atoms are balanced. We next have to balance charge. As you can see, we have 4 positive charges and 1 negative charge. So overall, we have 3 positive charges over here. To balance out the 3 positive charges, we need to make sure that we have 3 negative charges or 3 electrons on the reactant side. If I have 3 electrons on the reactant side, we know that this half reaction is going to represent reduction. For this half reaction, we have 2 negative charges on the reactant side, and then we have 4 negative charges here because it's 2 times 2. That's going to give us 4 negative charges. We also have 4 positive charges. So the question becomes, well, how am I going to balance the 2 negative charges here? We're going to have to make sure we add 2 negative charges on the product side. So if we're adding electrons to the product side, then this is going to represent oxidation for our half reaction. Now that our charge is balanced and everything else is balanced, we can just go ahead and rewrite our half reactions for reduction as 3 electrons plus 4H plus MnO4 minus on the reactant side is going to produce MnO2 plus 2H2O for the product. And then for the oxidation half reaction, we have 2H2O plus C2O42 minus is going to produce 2CO32 minus plus 4H plus 2 electrons. Now for step 3, the next thing we have to do is multiply each half reaction, if necessary, by an integer so that the number of electrons lost and gained are equal. So for us, it definitely is necessary because as you can see, we have 3 electrons that are going to be gained and we have 2 electrons that are going to be lost. So in order to find an integer that works between them, we can look at 6 electrons, for example, and we can multiply this half reaction by 2 and multiply this half reaction by 3. All right, so for our reduction half reaction, we can now have 6 electrons plus 8H plus 2 MnO4 minus is going to produce 2 MnO2 plus 4 H2O. And then for our oxidation half reaction, we have 6 H2O plus 2 C2O42 minus is going to produce 6 CO32 minuses plus 12H plus 6 electrons. Now for step number 4, our goal is to add the half reactions and cancel substances that appear on both sides. So I'm going to take this reaction here and this reaction and add them together. All right, we have our 2 half reactions. So let's go ahead and get rid of things that are the same on both sides. We know our electrons are the same. We also have 8H plus here and 12H plus here. So we can get rid of this 8H plus and we'll have 4H plus left over. We also can look at our water molecules. We have 4 water molecules here and we have 6 here. So we'll have 2 water molecules left over. Now all that's left to do is basically write down what's left over. So over here, we're going to have 2 H2O left. Then we're going to have 2 C2O42 minus left over. Then we're also going to have 2 MnO4 minus. And then on the product side, we're going to have 2 MnO2 plus our 6 CO32 minus plus our 4H plus here. And that's pretty much it. We already got rid of our 6 electrons. All right, folks, couple things. So I did change this to a 3 C2O42 minus. That should be a 3 in front of there. All right, folks, not a 2. All right. If this was going to be balancing a redox reaction in acidic solution, all we would do is step number 5 and check that everything is balanced as far as charge and as far as every single atom with this overall reaction, and we'd be done, right? But because we're balancing a redox reaction in basic solution, we do have one more step, and that is to neutralize H+. So when we look at it, we have H+ on this side here. So we need to make sure that we're adding 4 OH minus here. When we add 4 OH minus, that's going to create 4 water molecules on this side. Since we added OH minus onto this side, we have to add OH minus onto this side. So that means we're also adding 4 OH minus to this side. Now we have our overall reaction that we can write out. We want to make sure that we, of course, are getting rid of things that are the same on both sides. When we look at everything here, we see that we have 4 water molecules and 2 water molecules. So I can get rid of the 2 water molecules here and only be left with 2 over here. Now all I have to do is write down everything that is left over, and that will be my final answer. So here's our final answer. Of course, I've written everything that's left over down, 4 OH minus. I have the state of matter aqueous plus 3 C2O42 minus aqueous plus 2 MnO4 minus aqueous. That's going to produce 2 MnO2 solid plus 6 O32 minus aqueous plus 2 H2O liquid. Now, some folks might say, well, how am I going to get all these states of matter? First, always refer back to your reaction. A lot of them are already given to you. As far as OH minus and H plus, those are always going to be aqueous ions. And then for water, that's always going to be a liquid. Okay, folks? Other than that, it should be given to you in the overall reaction. The next final step is going to be step 5, which is checking the charge and that everything is balanced. So let's go ahead and look at charge first. We have 4 negative charges plus 6 plus 2. So that's going to give us 12 negative charges on this side. And then we have 12 negative charges on that side. So our charge is balanced. Let's go ahead and look at carbon atoms. We have 6 here, we have 6 there. We're good. We have 18. We have 18. Looks like we have about 24 oxygens on this side, and we have about 8 plus 4. That's going to be 12. Okay, plus another. Yep, we have 24 oxygens on this side as well. Looks like we have 4 hydrogens and 4 hydrogens, and then 2 manganese and 2 manganese. So we are completely balanced. This is going to be our final answer. It has all the states of matter, and we are good, folks. So we have successfully trained and learned all about redox chakra and used our new jitsu, the half reaction method, okay, to balance redox reactions, of course, in acidic and basic solutions. I think it's time we get our first mission. So Kakashi is going to meet with our leader, the Hokage, or Lord Chemistry, to see what mission we can receive, folks.